We got to make them understand that we need them more than they need us, okay? In fact, if you guys are really sharp, you'll figure out how to go down there every Monday at 3:30 and say, hey, can we buy your leftover lunch stuff for 30% off, bring it up here, and hand it out to everybody, right? It's good use of IEEE chapter funds, right? Okay, thank you. All right, thanks.
Well, to wrap things up, Andrew Stillwell is going to talk about a distributed grid analytics platform for residential phasor measurements. So it's a DGAP, right? Okay.
The DGAP.
The DGAP. So Andrew is a graduate of University of Missouri, Columbia, not wrong, Columbia, and worked for about 4 years at National Instruments, correct?
Closer to 80.
Closer to 80, my bad. Okay, so we're just grateful to have Andrew, and then we'll do the elections after this.
All right, thanks, Chris. So passing around is an actual piece of the hardware, so be careful with it as one of 4 working prototypes, mostly working prototypes. Let's see if we can get this started. Okay, so this basically is a single-phase PMU, so we'll talk a little bit about phasor measurement units, why we're looking specifically at the distribution level, and then we'll go into basically how this works, what it does, what are some of the advantages of it. Oops, go try. Okay. Let's see if we go back now. Why am I not working, Kevin? There we go. All right. So I'm kind of preaching to the choir here when I talk about phasor measurements, but when we're looking at phasor measurements, we're measuring the voltage or potentially current. When we do this, we have to do it at a certain frequency, and then we calculate the RMS magnitude, we calculate the phase, we also calculate the frequency of the signal. We have to timestamp the signal, so we actually care about when the phase occurs, when we're looking at the frequency. We want to look at this correlated in time. And then finally, you have to transmit the results. So you have to send them out to a server or some central data collection service so that you can look at multiple points throughout the US grid or the world and find useful information or trends. So if you look, my focus is very much on the distribution level. Transmission level right now is very part of the utilities, right? When operators are out there, they have a very good idea of what the phase and magnitude of their voltages are at different locations. They do the PMUs at the transmission level. So high voltage, very expensive measurements, but they're distributed all over throughout the grid. Utilities have access to this. Typically, we as researchers in academia do not. For distribution level, though, the cost of entry is a lot lower. You already have the power in the area where you need that you can use for, say, powering your device. You don't have to step down or put out a big battery out there. So if you're talking about residential or in-home measurements, you already have Wi-Fi, you already have AC power, you can take measurements at a very low ceiling. And so this is pretty attractive for academia where we want to put out a lot of these. Also interesting for industry if they're having brownouts or fluctuations at a small level and they really want to get down to where the problems happen, they can take these measurements at that point. All right. So one example of this is the frequency disturbance recorder, FNet. So a lot of us have seen these. We've got one of these boxes in our lab, actually a few of these. I think Desiree has been working with these distributed throughout Champaign and a few other areas. So like Dr. Sauer's always talking about the one at his house. But the challenge with them is they're still expensive. They're about $2,000. Although they've gotten to the point where they're trying to get more of these distributed, so they'll actually give them away to you if you're living in, say, Seattle. So if any of you are taking a job there, you want a box, they'll probably give you one. But this is a very fixed platform, so it does one thing. It measures the phasors, and it records it, and it does it very well, but that's all it does. And as far as any of the other capabilities, it's not a particularly high sample rate, although this is pretty standard for PMUs. And it doesn't have auxiliary power, meaning if the power goes out in your house, this box goes down to it. It's got one line going into it. That's what it measures, and that's what everything's powered up of. Which, for us, we're really interested in when it goes down, just before it goes down and just after it goes down, what is the voltage actually doing? as a waveform level, and also as the frequency oscillating or doing anything interesting like that. So this is one of those challenges for us. However, they do have a really good infrastructure when it comes to the number deployed, and then they've got some pretty interesting visualization built out there. So they've got a good database and a good start, and we want to kind of take advantage of some of these things as well. Right. So if you look at the needs, there's from the academic point, there's lots of things we need from one of these measurement devices. Distributed is kind of obvious. We need to be able to deploy lots of these all over the place. We need high performance. We need something that's very open platform. So from the academic standpoint, having a box that just does one thing is not as attractive as having a box that I can go in and change and write better code for, because I'm sure there's lots of people out there that can write a better frequency algorithm than me, or wants to do something very interesting with the box that we never thought of. So we wanted to have a very open platform. Onboard storage is important. Being able to have a battery backup is important for the reasons I talked about before. Low cost is kind of an obvious one, but at the same time, when we're talking in terms of $2,000, we're looking for something we want to deploy for $200. So we can put 10 of these out there for the same cost. And then secure. We want to make sure that the communication is secure and no one rides into it. And industry is very similar to this. They're less concerned about the open platform. They're much more interested in, okay, if I deploy this, is it going to do the same thing over and over again? As long as that one function that we give them is what they need, then they're going to be happy with the device. Right. So that's what we set out to build. And by we, I mean Yuchi, who's not in the audience, worked on this a lot. We also had some help from Dr. Ogilvy's group. But this is the Distributed Grid Analytics Platform, or DGAP, as Chris pointed out. But it's distributed. It's Wi-Fi or Ethernet. Wi-Fi is an optional add-on. It's very high performance. Right now we have a 14-bit ADC. It can go up to 20 kilosamples per second, potentially higher if we can get the system optimized. Very open platform. So this is basically a PC running Linux on it. And so everything under there is running code that we've written, and that can also be rewritten or customized for you. Lots of onboard storage, has a lithium-ion battery backup, so it can measure when the grid goes down, and as long as the grid comes back up within a reasonable amount of time, we'll have stored that data and we can transmit those results once we have the internet back.
What is that reasonable amount of time?
I think right now it's about 30 minutes, but some of that depends on how big that battery is, and we haven't really optimized for power, so we could turn off certain peripherals if needed.
So it's a battery limitation, not a storage limitation.
Yeah. And storage is very flexible here, so there's a micro SD card slot on there. We could add 64 gigabytes of storage on there, and we're not really going to be pushing up against that unless we're going a long time. And then secure. So again, the data will be encrypted, so when we're transmitting that, it can't be written into very easily. So looking at the architecture, hopefully you all have seen the box riding around, but basically the heart of this is this single board computer. It's a Texas Instruments BeagleBone Black. I'll talk about it a little bit more in a bit. But it basically provides a lot of what we need. It plugs into the battery charging circuit, but essentially we've got voltage coming in, we have a step down, an isolated analog to digital converter going to the single board computer. We take power from this same 120 volts, and then this is basically just your USB plug or something along those lines, giving us 5 volts power. And then we have battery charging. GPS is needed to give us time synchronization to know exactly when we're taking the measurements, and also kind of check our clock stability. And then of course there's storage on there. And hopefully I can get to the next slide without skipping over 5. There we go. Okay, so the heart of this is the BeagleBone Black. You can think of this as it's very similar to the Raspberry Pi or really your cell phone. It's an ARM Cortex A8. It has pretty decent memory on there and pretty decent storage. The microcontrollers are actually extremely useful for this because we take advantage of both of these microcontrollers. They give us very deterministic timing, one to synchronize with GPS and another to provide the signaling for the ADC to make sure that that's going at a deterministic rate. But since it is a computer, it also has things like a USB host, so we can put in a Wi-Fi dongle and now we have Wi-Fi. Or we can put in a keyboard for debugging. More realistically, we could also do more expandable storage off of this if we needed to outside of the micro SD card. It has lots of I/O. One thing that's really useful is the large user community. So I'm not much of a Linux programmer. I'm not much of a assembly level programmer, but there's some good code out there to start with, some pretty good tutorials out there, and a lot of code to leverage when it comes to what you're looking for. Yes?
Is that USB port, can you provide power through it, or is it strictly data?
So there's two USB ports. There's one that's basically an input USB port where you can either talk to it over basically an Ethernet port, or you provide power. And then there's a peripheral USB port where you can plug in a thumb drive, a keyboard, or anything else along those lines. So there's both like a host and a controller side for the keyboard.
Okay.
Or for the USB.
So is your backup battery, is it plugged into one of those, or is that external circuitry?
There's some external circuitry. There's basically, let's see if we can pick it out on here. So these 4 pins right here by the 5-volt supply we take those leads and hook it up to a little battery charger basically, and the battery itself. There is battery charger circuitry built into the BeagleBone, but we haven't tested it yet. We had some initial, we looked at some forums where some people were saying it wasn't working, recent ones saying it is working.
Yeah.
So it's something we may be able to leverage in the future. All right. And $55 cost for basically a pretty decent little computer, which works well for our purposes. So looking at the software, I don't need to go through all of this, but basically we've got the ADC coming in. We have the onboard microcontrollers, which everything there is written in assembly. That uses shared memory to the DDR and talks to a C program, which basically C is acting as a big buffer and sending it to Python. Python does the actual guts of the work. So it's actually taking the frequency measurement, looking at the phase, doing all the control, and then it transmits it over Ethernet to this open source PMU data handler. So there's an open standard for PMU information. The big thing here is that if you wanted to write your own algorithms for either analysis or anything along those lines, all you'd have to do is touch the Python code. You wouldn't have to touch the assembly or the C or anything else along those lines. Python's very easy to upgrade and to send out things over the air. So Python is kind of our algorithm development. Everything else is more of background running underneath the hood. Hopefully you don't have to touch it unless I messed something up. And then, of course, with GPS, we talk to it over UART, and that gives us the timestamp information and gives us a time source to synchronize off of. So we have some very initial results at this point. I'd love to have more, but I'm still working on them. This is this PMU connection tester. Again, this is kind of an open source message handler, and it's using a standard IEEE C37.118 is a PMU, basically a synchrophasor standard, and we are compliant with that. And so you can see here we're logging results. We're right at 60 hertz. Our phase is changing a little bit over time, which is expected. And that's about it. But at this point, we're able to log over Ethernet and give us good results and go forward with that. We're still working on some long-term reliability and some of the data handling. But at this point, we've got a very good vertical slice working and functional. So some of the specifications, right now we're fixed at about 120 volts RMS, but we're looking at extending that range a little bit more so that we could, say, do Europe. Our ADC resolution is 14-bit. Sample rate right now we're at 10 kilosamples per second. I'm pretty confident we can get 20 kilosamples per second, but some of that is relying on some of the buffering and going between C and Python that I'm not keeping up as well as I can, so that's still working. The Phasor sample rate right now is fixed at 20 samples per second, but if you look at that standard, depending on whether you're at 60 hertz or 50 hertz, you need to be able to support all of those Phasor sample rates. So the rate at which you return the frequency, phase, and the magnitude is something you're supposed to be able to set. And right now, just that hasn't been implemented in code. Size is still pretty small. Hopefully you all got a chance to see the box, but I think we can hit smaller. And the material cost-wise, we're trying to get this down to about $100. We're pretty close, and especially at $120. That's a pretty good comparison to, say, the $1,000 or $2,000 FDR that's already deployed. There we go. All right, so just to point out a few things on flexibility. with expandable storage, you can turn this into a remote logger. And so say you don't have internet or 3G coverage, but you still want to look at a node for a long period of time. You can put expandable storage on here as long as you have power. You can log for a very long amount of time, especially if you're only looking at the Phasor measurements as opposed to the raw ADC data. One thing that we've noted is there are people have deployed GSM with the Beagle Black as just another peripheral. And so that is a capability of where if we didn't have internet but we had 3G coverage, we could deploy that. The analysis is really very flexible. As I mentioned, right now it's in Python code. It could be written in C code. The analysis I use is pretty off the shelf using a lot of built-in Python functionality, but if you had something very specialized as far as what you were looking for, you could run your own algorithms on this. And then there is additional I/O on here that we're not using, but I'm planning on trying to break out in the next one. So if you wanted to do some very basic control where you're toggling things on and off based off your results, you could do that as well. All right, so summary, the DGAP, basically right now it's measuring 120 volts to 240 volts. Very flexible, has good storage, communication, everything else along those lines, and the big thing is low cost. All right, and then with acknowledgements, I got to point out, Yuchi Lee, I mentioned this earlier, she did a lot of this hardware, especially when it came down to the PCB and putting it in this nice box, which might be the most impressive thing about the whole part. But Chris Drew also wrote a lot of the Python backend code. So as far as communicating to the standard, he did a lot of his work. He's working with Dr. Overby's group. The Illinois Center for Smarter Electric Grid and the Granger Foundation for funding my work. So I'll open it up for questions. Srikanth, you had your hand up first.
Okay, a couple of questions. Can you talk a little bit about the algorithm which is used to compute the frequency, the fundamental frequency? And second one is, in the presence of harmonics, how is the algorithm going to behave to extract the fundamental frequency component?
Okay. So yeah, the question is, what is the algorithm for calculating frequency, and then in the presence of harmonics, how does the algorithm handle that? So this is a pretty straightforward method. It takes an FFT, and then it does basically a curve fit on looking at the different bins, and calculates the fundamental frequency off of that. So there are some known issues with that when it comes to harmonics and things along those lines, and I haven't fine-tuned some of those things. But for what we've looked at and what I've benchmarked it with so far, it's doing well. But it will need more work before it's ready for prime time. And there are several algorithms out there, like the University of Tennessee and University of Virginia Tech that did a lot of the FDR. They've actually done a really good job of publishing their work on what they've gone into that, and we're definitely going to leverage some of that code. But it's an excellent question. It's not an area of strength for me, but one that we're continuing to build up.
Okay, the reason why I asked is there was a method in power systems transactions a few years ago. It was an elegant method of nonlinear least squares based estimation of power system frequency. It basically expresses because in India there is always a problem of harmonics. We never get sine waves at all. We get trapezoids. So to extract that, there was a power system frequency estimation method where f of x is sampled at a certain for overestimated set of equations and express the f of x as a Fourier series, and then we don't know the value of theta, and which is basically corresponding to frequency. And then this is sort of a nonlinear least squares estimation is done, and the curve is fit, and then the place where the minimum error is found is the fundamental frequency. Maybe I think that would work really well in your algorithm as well. Yeah,
it would be worth looking at. What I'm finding is it's always a trade-off between computation and sample rate and the amount of data I'm processing. And just also a fundamental limitation of, if I want to spit out 20 measurements a second, I can only look at a 50 millisecond window, and I've got to get my frequency from that. And that becomes a limitation when you start using FFT-based operations. I've also looked at autocorrelation, things along those lines. Honestly, at this point, I found a pretty good algorithm off the shelf. I made sure that it worked for my scaling. I understand the limitations of it that I need to work around, or I need to continue to look at other algorithms. things. But there's some really good papers on that. I'd be interested in seeing that.
Yeah, I'll send it. Thank you so much.
Yeah, I want to emphasize to everybody, you can't just watch zero crossings and get the time, right? Because you're completely at the mercy of any distortion of the waveform. The SD card looks like it's effectively being used almost like a hard disk.
Correct.
Well,
It could be.
we certainly have experienced an unnamed manufacturer who was using this for a very similar application in the field. You know, those little cards really are not made for that many read-write cycles. And they were finding that they could kill them in a few weeks. In fact, they were finding all kinds of field failures that nobody could figure out until they realized the cards basically were getting burned up because they were being treated like hard disks. So they had to spend a lot of effort rebuilding their algorithms so that they were kind of minimally writing to the SD card, and basically it's getting refreshed, you know, once a week or once a month rather than, you know, once a second, so that they can keep them running for years and years. And that's a very non-trivial activity here. I guess, so, you know, you answered that question, and that's a comment. The other one, you know, obviously any backup, any secondary battery you can put here is ultimately going to wear out. Not ultimately, it's actually going to wear out pretty quickly. Primary battery, UltraCap, any thoughts about those kinds of things? Because you only need it to be running basically for a few seconds as it dies, and then come up quickly enough to get going once something comes back online, sort of, right?
Yeah, so you're right. For the most part, we don't envision this battery powering this for a long period. It should be in the case of a quick blackout, or, I mean, if in the case we're down for a few hours, then, you know, we're probably just going to log what we have to a hard disk and then try to shut down the restart. I haven't focused as much on the battery, and the lithium polymer one is a good, convenient one that fits within the charger that we have and the space constraints we have. But I think we do need to consider a little bit more what the ultimate use case is for this, and where we really think customers of this really are going to have the value. If it's just, okay, we have a quick blackout and we still want to record, what we have is probably suitable. I don't foresee a lot of discharge and charge on this. It's more of a long-term, it needs to stay charged, and then it discharges, you know, it needs to stay.
I'm curious why you say it'll wear out.
Oh, it'll wear out, yeah.
Well, because because it'll make it discharge twice.
It'll wear out just based on time and environment, right?
Well,
Any of these
that's a
secondary
long
batteries.
time, right? That's a long.
Well, I wouldn't bank on that. We're not seeing that with real lithium batteries. But if I were you guys, I would think about using a primary lithium battery that really will last for 20 or 30 years, and you get those few seconds you need when it goes out, and then you say shut down, and as soon as you see anything, you say, okay, come back up, start over again. Now you got a battery that'll last for decades that you don't even have to think about.
Yeah, but I think that the purpose of this is not to be out for 30 years in the field, right? This is more of a, hopefully no longer than Andrew will graduate.
Yeah, but any rechargeable battery, you're at the mercy of whatever its operating life is, which is.
No, but that's the point. It doesn't discharge.
Well, I understand that, but it's not just charge-discharge cycles that wear it out.
No, but
Just like capacitor.
Yeah, but they ought to be good for about 5-10 years, right?
Yeah, good luck. Anyway, okay, I was very curious about those two things.
I guess one thing to note on the SD card, right now, there is built-in storage with the Neolum Black that we right. And then there is the SD slot that's additional storage. So for the most part, we're not using the SD card yet, but that is a good point that if we are going to rely on that, we need to take that into consideration.
Right, and what you think about that is using RAM all the time until you hit that power glitch, and then dump everything in RAM into that SD card and shut down basically.
But there's onboard storage on the device that's non-volatile.
Right.
Sure.
Have you been able to assess the accuracy of the measurements?
So frequency is good. We're within like 5 millihertz at 60 hertz with a pretty good, clean, calibrated sine wave. The voltage measurements I'm still working on. So for example, with a pretty good calibrated source, 120 volt RMS, we're 120.03 volts or something along those lines. And that's not a particularly detailed calibration at this point. I'm still in the lab measurement stage. But with 14 bits, what we have, we're on the order of our competitors, and we should be able to meet the spec requirements.
What's the source of those errors?
Calibration that I'm doing. So I don't have a very good source at this point that I'm putting in, and I'm literally just taking 2 points. So I'm very much still in the development stage. And so when you just take that 2-point calibration, you're not looking at any other non-linearities or any drifting components once you get to larger ranges. I should be able to get very good, but I haven't really dived into everything else that might be contributing to it. Sure.
Have y'all talked with utilities and gotten like their feedback on like what do you want to see, what type of accuracy do you want to see, or like what price point do you want to see this device at?
So a lot of our primary customers so far has been ourselves, Dr. Overby, Dr. Sauer, and that's driven a lot of this. When it comes to accuracy, the spec lays out what the accuracy needs to be in order to be spec compliant, and our goal is to be spec compliant. And as far as I know, there's no need to go beyond that. Otherwise, we probably would have gone with more focus on the ADC and potentially.
So I guess like the future of this, do you see it growing into a business, or are you not concerned with that part of it? You want to do your research and be done with it?
I think there's potential for it. I think there's certainly customers in ourselves for it, whether this turns into a spinoff or whether we just manufacture these here. I'm not less concerned with at this point. I've spent most of the semester just getting it working and writing assembly code and C code, which I haven't done in 10 years.
Yeah.
But I think there's some interesting applications just in general for this platform, not only with grid monitoring, but something more deployable. Anytime you have a nice 120 volt front end and the tools to be able to measure it and do interesting things off of it, you start getting into a little bit more of the smart devices type area. And as a development platform, you can do some interesting things with it. I'm not sure if I answered your question. But
Yeah, that's good.
Sure.
From a thermal standpoint, is there, or maybe it's not a thermal standpoint, is there a reason why the box is so much more luminous than the board itself? Is it to allow for convection inside?
That is a very good question. No, we chose a box that fit about the components we had. We haven't optimized that. Honestly, we chose a nice off-the-shelf box that we didn't have to put a lot of time in because none of us are mechanical engineers. And I think that is something we want to look at moving forward. I think something smaller and probably a lot more manufacturable. I mean, right now everything else is mill that light. And that works great for prototypes where we're doing 4 or 5 of them, but if we got a nice grant to deploy 50 of these, we have to rethink that. And the goal is to be able to deploy in the larger numbers. So something more custom is probably what I'm working on as well.
Yeah, Professor Overby mentioned that was actually quite expensive, the housings, and I was curious, like, why didn't you 3D print them?
So, okay, the boxes themselves were cheap. They were $10. Getting them milled out with the Z-score was expensive.
Yeah.
And that's just there for prototypes, and these are prototypes. We could have 3D printed these. I like the finish and fit of this box, but we absolutely could have 3D printed these. Going into larger quantities, you start looking into custom molding, and there's actually some pretty low-cost suppliers that I'm looking at here that'll do. They'll do the punch outs, they'll do silk screening, everything else along the lines of what you need, and they can do it for about $10. And so once we get into quantities of closer to, 100, something like that makes a lot more sense. But we just need something that works, that looks good in a box, and that we can test without having to worry about wall voltage being exposed. Yeah.
For frequency, is it conceivable that at the right location you can pick up radiated EMI without running something to the wall, say next to a power line? Again, my question is, how long before my my phone can do something similar. If I'm next to the colleagues coming to the house, that's something I can pick up. Voltage may be higher.
Yeah. I'm not familiar with sensors that would do that at this time. Looking at EMI at that level with your phone or something else along those lines, I mean, there's current transducers, right, that you could latch around a cable and definitely pick up what you need as far as measuring EMI and getting a good sense for voltage, magnitude, phase, and have a good synchronization. I'm not sure. All right, I think that wraps it up. Thank you. Thank you.
Okay, so now we'll quickly have the elections for the next year's IAS